Thank you for that introduction and for the invitation to speak. Yeah, also actually, I'll actually be moving quite soon to Germany. So maybe at some point we can visit at some point when I'm out there. Okay, yeah. So today I'm going to talk about this this thing called the Ceresa class in these three different settings: the tropical setting, the topological setting, and algebraic. And this is joint work with Jordan Ellenberg and Wanlin Lee. Okay, so I'm going to start with describing the sort of origins of this this object, right? And this is this comes from a sort of algebraic cycle called the Ceresa cycle. So the setup is the following. So suppose we have X defined over some field of characteristic 0, K, and X is some curve. And for the beginning of this talk, let's maybe think K equals complex numbers. And soon we'll change this to C double parentheses T. And then so to this algebraic curve, we can define an algebraic cycle. Right, you can take, so you take your curve X, let's say it's like genus, like, I don't know, bigger than or equal to 3. I guess we could do this bigger than or equal to 2, but we'll soon see that nothing interesting happens for genus 2. And so we can take its class inside of the Jacobian via the Abel-Jacobi map. Okay, then inside the Jacobian you have this, right, the Jacobian's a group, you can act by -1. So you can do that to your algebraic cycle. So this is some algebraic cycle in the Jacobian of X. And this is this thing called the Ceresa cycle. Okay, so why is this cycle interesting? Well, it turns out that the Ceresa cycle is homologically trivial. Right, so this is basically due to the fact that this -1 action acts as the identity on the even homology groups of the Jacobian. So these two define the same homology class. But, and this was the big theorem proved by Ceresa in the 80s. The cycle X minus -1 X is not algebraically equivalent to 0.
Can you just repeat what the -1 map is again?
The -1 is like on the it's the -1 action on the Jacobian. So I guess, right, if you're fixing like a point P on your curve X and you're embedding by like right, the point Q goes to Q minus P, right? This gives you, right, the X inside the Jacobian, then the -1 on X gives you the other embedding, right? Q goes to P minus Q.
Oh, okay, thanks.
That's probably another better way to think about this. Okay, so the theorem from Ceresa in 1983 was that this algebraic cycle is not algebraically equivalent to 0 for a very general curve X of genus at least 3. Right. So the significance of this is that, right, it's sort of one of the easiest cycles to define that's homologically trivial, but right, for I guess for a very general choice of X is algebraically non-trivial. So it's this one of the simplest cycles that goes beyond homology in this context. Right, and so maybe I can comment why genus at least 3, not 2. Right, it turns out this Ceresa cycle is it actually is algebraically trivial for hyperelliptic curves, right? And if you take this point P that you're embedding by to be like a Weierstrass point, then I believe that these two cycles end up being the same, and then they'll cancel out. And so otherwise, if you embed by some other point, then these two cycles will just differ by some translation. Okay. So our interest is not going to be this exact, well, our interest, well, I guess partially is this cycle, but we're going to study this cycle by looking at a particular cohomology class associated to the cycle. So our interest is in the image of the cycle under this L-adic Abel-Jacobi map. Right, so here is really where we're going to start becoming interested in the case where the ground field is C double parentheses T. Right, and so this will produce a cohomology class in the following group. So we'll call this class nu upper L of X. And this is going to live in this group H1 gal K bar over K, right? So the absolute Galois group of C double parentheses T, right? So this is just going to be Z hat for this case for K equals C double parentheses T, with coefficients in LZL mod HZL. And let me define what these spaces are. Right, so here, let's see, we'll do H first. So H ZL, this is the first étale homology group of X tensored with K bar with coefficients in ZL, say twisted by 1. LZL is just going to be this third exterior power up to some Tate twist. And then, well, we can actually, right, so here I guess we have to describe how is H living inside of L, and H is living inside of the third exterior power by just taking a wedge product with this intersection 2 form on H, right? So this H, I guess you can think of as like, dual to the first, the way I think about this usually is it's dual to like the first homology group for a genus G surface, and then you have this intersection pairing of curves on your surface, and so this signed intersection pairing can be realized as like a differential 2 form, right? So maybe I'll just comment right H Z L, and then I guess we're doing like a sort of L-adic analog of this intersection 2 form. Right, so omega is this intersection 2 form. Right, we'll see a little bit more of this explicitly when we get to the topological setting. Okay. Right, so we got, right, so this class that we get here is what's called the Ceresa class, or the L-adic Ceresa class. I don't want to say too much exactly like how we get maybe the space here. We'll see when we get to the topological setting a better interpretation for what the space is. Well, if you're coming from topology, you'll see, you know, this might look familiar. It's the target of the Johnson homomorphism, and so you know, and we'll see how that comes up in the topological setting. Anyway, so the significance of this Ceresa class is that, or I guess nu L of X, right, is that the Ceresa, original Ceresa cycle from above, this is going to be rationally not equivalent to 0 whenever this class is not equal to 0. Or I'm mixing up the grammar here, is not rationally equivalent to 0 when this class is not equal to 0. Great. So sort of motivating question for us was the following. Right, in what sense can we carry over this notion of a Ceresa class to tropical geometry? And you know, can we use tropical geometry to actually study this original or the Ceresa class as I've defined here? Okay. Right, so this brings me to the next part. So this is, I'll call this section degeneration. Right, so in answering this question, we're actually able to define a suitable notion of a Ceresa class in two separate settings: this topological setting and the tropical geometry setting. Right, and all of these settings will be related to, or we're going to look through we're going to look at all of these settings through the lens of stable degeneration. And so more than that, more than just sort of developing an analogous notion of a Ceresa class in these two settings, we're actually relate right, the Ceresa class in these settings to the original definition. Okay. Right. Okay. So these three settings are going to be related to each other, or we're going to view degeneration in these three different settings. Okay, so first there's, or let me maybe describe the setup. Well, so we have a holomorphic, or hold on, let me say that we have maybe a family of complex curves over this unit disk in the complex plane. And let's say it's holomorphic over the punctured disk. And then let's say over 0, the curve is a stable curve. Okay. So I'm going to describe what stable degeneration looks like from the perspective of topology, tropical geometry, and then algebraic geometry. Okay. Right, so in the topological setting, you forget about any sort of algebraic structure you have. You just care that these, you have a smooth map who's over the punctured disk. Of genus G surfaces. Genus G topological surfaces. Right, and so my understanding is the way like a topologist thinks about this sort of degeneration is you forget about the actual curve at the singular fiber and you study the monodromy action around around the curves around that singular point. Right, but when you do have this stable degeneration, the monodromy action on you can think of it, I guess, either on the mapping class group or on the action of the mapping class group on the outer automorphism, the action on pi 1 of the genus G surface is given quite explicitly, right? So say we have, a genus 3 surface, and then say, right, this is some smooth family over the punctured disk. And then let's say it degenerates to a singular curve whose dual graph is the graph K4. Right, so you can think of this as maybe you look at these orange curves and you pinch them to 0, and then you look at the dual graph of this curve and you get a K4. So it turns out that the monodromy action then corresponding to this this family of curves over the punctured disk is just going to be equal to a product of commuting Dehn twists. Right, so the action's just given by a product of the Dehn twists around, you have a Dehn twist around one for each of these curves, right? And well, you have to figure out the power that you raise these to, and that powers can be read off. We can see this from the a little bit easier from the tropical perspective, but it sort of depends on how the actual family of curves is degenerating into the singular curve. Right, so now from the topological geometry perspective, this data of degeneration is recorded in a metric graph. Strictly speaking, a vertex-weighted metric graph. Recording the stable degeneration. Right, so the picture that that we have here is, well, you have, right, the way this graph is supposed to look like, it's the underlying graph is going to be the dual graph to the stable curve. So in this picture, we have 4 irreducible components corresponding to the 4 chunks here. And then you have an edge between each curve that shares a node. And then, in general, right, you could have, right, the vertex weights here will come from the whatever the, presumably you could have like a genus in one of these components, and that the vertex weight would just record that genus. And then the lengths again come from how the curve actually degenerates into the stable curve in the center. Right, and then finally in the algebraic geometry side, to describe all of this data, you're just describing a curve, right? X defined over C double parentheses T. Let me call this that K. Okay, so in each of these settings, there's a sort of combinatorial piece of data that we're going to assign the notion of a Ceresa class to. So here, in this setting, the topology setting, the piece of data we're going to assign the Ceresa class to is, well, this monodromy operator. Right, so here it's going to be this multi-twist. In the tropical geometry setting, we'll define the Ceresa class for it, just the graph itself, or together with its weights. And in the algebraic setting, right, it turns out that the Ceresa class doesn't depend on the full curve itself. It just depends on the action of the Galois group on the étale fundamental group of X base change to K bar, or base change to K bar. Right, so I guess the motivation for this was an observation that this L-adic Ceresa class from before only really depends on this data here, right? And this is sort of maybe philosophically just the data of monodromy, and so this should extend into these two settings. And so this is what we do, and I'll describe how we do this, but it turns out to be more than just sort of an analogy how we define the Ceresa class in these two settings. They actually are precisely related to the Ceresa class in this setting. Right, so the plan now is to define the Ceresa class here first, and then we're going to show how it induces Ceresa classes in the other two settings.
Hey, Dan, can I ask a quick question?
Yeah, what's up?
I mean, in principle, there's like a whole class. I mean, there's a whole class of degenerations of a curve, and then there's some other class of Dehn twists that I can do. Are those like, I don't know, are there roughly the same number of those? Like, do they match up? Like, is every Dehn twist, is every multi-twist coming from some degeneration?
Yeah, I believe so. Yeah, that should be the case.
All right, thanks.
Yeah, and I think like maybe a way maybe to make this precise is like at least the way we did this in the paper was we looked at like this like analytic local universal family and this algebraic local universal family, and so you can realize any one of these like commuting Dehn twists. You look at like the powers that appear there, and then you pull back under, from like a map on the on like the base spaces of like a curve, say like passing through 0, where you have like t to various powers in the coordinates. And you do this on like both the algebraic and the analytic sides. And if you do this on the analytic side, you get something that's produces this like monodromy operator, which is this product of commuting Dehn twists. And then on the algebraic side, you get you'll just get a curve whose tropicalization is your prescribed metric graph.
Oh, great, thanks.
Okay. So now let's define this topological Ceresa class. Right, so here we're going to now just be entirely in the realm of surface topologies. So I want to maybe take some time to define some notation and recall some notions from surface topology. Right, so we're going to let sigma g denote a genus G surface. We're going to let gamma g denote the mapping class group. And on your genus G surface. And then so if you have, say, L a loop, or like maybe let me phrase that more precisely, a simple closed curve. In on your surface sigma G, right? We denote by T sub L the Dehn twists around that loop. Right, so now if you're given some collection of pairwise non-intersecting loops, right, this allows us to form this multi-twist. Oh, and let's say you're also given positive integers, CIs. Right, then we can form this multi-twist T sub capital lambda, and this is just the product over these TLIs to the CIs. Right, and so notice that there's no ambiguity in this product, because if you have the two disjoint curves, then their corresponding Dehn twists commute in the mapping class group. So it doesn't matter how we actually form this product. Okay, so now so what I'm sort of veering towards at the moment is I want to define the Johnson homomorphism for from topology, and we're going to use this Johnson homomorphism to define the Ceresa class. So let's let H be the first homology group, and then L is going to be the third exterior power of the first homology group. Right, so these are entirely analogous to the H and L that were defined previously. So just keep this in mind as we go through. Right, and so as before, right, H embeds into L by sending H to H wedge this intersection to form coming from your surface. Okay. So now let's define the Johnson homomorphism. Right, so this is a map we'll call J from the Torelli group I sub G to L mod H. Here, right, I sub G is the Torelli group. Right, so this is the subgroup of the mapping class group of mapping classes that act trivially on homology. And so there's this, we have this this Johnson homomorphism defined by Dennis Johnson in the 80s. There's a way to actually define this without using coordinates, but the way I'm going to describe it is in terms of coordinates, because it's a way that's useful for us in doing our computations, and it's a easy way to just get your hands dirty with the Johnson homomorphism. So it's characterized in the following way. Right, so first note that the Torelli group is has generators given by Dehn twists over separating curves and Dehn twists over bounding pair maps. Right, so fact, Torelli group is generated by T sub gamma, where gamma is separating. And T sub gamma 1, T gamma 2 inverse, where gamma 1 and gamma 2 form a bounding pair. Right, this just, right, so gamma being a separating curve just means that if you cut along gamma, it separates the surface into two surfaces. And then a bounding pair is two non-separating curves, but when you remove both of them from your surface, the surface splits into two pieces, right? So from the graph theory language, this is analogous to like a bridge and then a separating pair of edges. Okay. So the Johnson homomorphism, so right, to describe, I guess, what the Johnson homomorphism is, it suffices to note, given the fact that it's already well defined, we just have to say what Johnson does on each of these two types of generators. Right, so if gamma is a separating curve, then the Johnson homomorphism is not very interesting. It just takes this to 0. Okay, but now for a bounding pair map, right, this is, you get the following. So you get the sum of these exterior bits, AI, wedge BI, wedge gamma 1, for instance, from I equals 1 to k, where here, how are these defined? Right, say we have our surface like this. So gamma 1 and gamma 2 form a bounding pair map. Right, so by like a change of coordinates principle, you can actually just map these two curves to the two orange curves here, right? And you just have some genus on one side and some other genus on the other side. And now, how are these AI BIs defined? Well, these are just defined to be, this symplectic basis on half of the curve. Right, so the AIs, A1 through AK. form one half, and then B1 through BK form the other half of the symplectic basis. And then here we have, right, gamma 1, gamma 2. Right, so basically what you're doing is you're taking the symplectic form on the largest symplectic subspace of the homology of one half of the, on this half of the surface. And right, you take that symplectic form and you just wedge with, for example, gamma, the homology class of gamma 1, right? It doesn't matter if we could have done gamma 2, right? Because these form a bounding pair, they define the same homology class. And right, I guess there's another piece of ambiguity, like we could have maybe tried to do this side of the surface, and that's right, that ambiguity is taken care of by modding out by H here in the image of the, or the codomain of the Johnson homomorphism. Okay. Right, so here was this was sort of an aside. So the final ingredient we need to define the Ceresa class is we need to fix some hyperelliptic involution. So let's let tau from sigma g to sigma g be a hyperelliptic involution. Right, so in the topological setting, this just means that this is an involution in the mapping class group, so it squares to the identity, and it acts as -1 on homology. Okay, so now let's define this class nu in the group cohomology of the mapping class group with coefficients in L mod H by sending gamma to the Johnson homomorphism of the commutator gamma with tau. Right, so notice, right, if you take any element in the mapping class group, right, and because tau maps to maps to the center in the right, the symplectic group on H, we have that right, I guess if you take the right, if you take the symplectic representation of this element, right, it's going to go to 0, right, because tau, right, the symplectic image of tau will just commute with everything, right? So that means that this commutator here acts trivially on homology and therefore lives in the Torelli group. So we can apply Johnson to that. Right, so now this is sort of like a universal Ceresa class. And so for a multi-twist, all you do is you just take this universal Ceresa class and you restrict to the subgroup generated by your multi-twist. Right, so nu of t sub lambda, remember this t sub lambda was our multi-twist. This is just nu restricted to the subgroup generated by t gamma, and this lives in H1 subgroup generated by t gamma with coefficients in L mod H. Right, but notice that this, right, so maybe here's a good place for me to pause and compare to the locations of this Ceresa class, this topological Ceresa class, to the L-adic Ceresa class. So notice here, this T sub gamma, this is just, this has, this multi-twist has infinite order, right? So this group here is just Z. Right, so we have a class in H1 T gamma, or H1 Z comma L mod H, right? And so from before, right, this L-adic Ceresa class was defined in a Galois group or group homology, where the group was Z hat, and then the coefficients were the ZL analogs of L and L mod H. Right, but at least in, I don't know, in the topology setting, right, this is something that's like super, super explicit. Right, I guess it's also pretty explicit in the L-adic setting where you have the coefficients in Z hat. But this group here is just isomorphic to L mod H modulo the action of T gamma minus 1 on L mod H.
So then, just to make sure, the way you should be thinking about this is for, like, by taking gamma to be like this Dehn twist corresponding to a generator of the monodromy operation, right?
Yeah, so we're taking, I guess, are you talking about this gamma here?
Oh no, the T gamma, the T lambda. Sorry.
Oh, the T lambda, yeah. Yeah,
Yes,
so this
yes.
is going to correspond to the monodromy operator.
All right, thanks.
And so I'll maybe state in just a moment how to make the relationship precise to the algebraic setting, but I'm now in the position to state the main theorem. So this here is called is what we call the Ceresa class for the multi-twist T lambda. Okay. Oh wait, sorry, before that, let me state the theorem. So the theorem that we proved is that nu of T gamma is torsion for any, I should say, positive multi-twist T lambda. Positive in the sense that we want the CIs to all be positive. The powers of the Dehn twists. Okay. So now let's see. I want to sort of describe the relationship now from the topological Ceresa class to the other two settings, and then maybe describe some, the significance of this class through some computations. So let's describe the relation to tropical and algebraic geometry. Okay, so to go from a multi-twist to Ceresa class, the L-adic Ceresa class for a curve over CETL parentheses T, right? So let me maybe phrase it as from a multi-twist to X over here, right? So we have this. So over here, the Ceresa class lived in H1 of right T lambda, coefficients in L mod H. Over here, we had right H1 of gal K bar over K. Coefficients in L ZL mod H ZL. Right, so in these two settings, right over here, this is just Z and this is Z hat. And there's this comparison morphism going in this direction. And we prove that this comparison morphism takes the Ceresa class of T lambda to the L-adic Ceresa class of your curve X, right? And I guess, so I guess I need to, there's this correspondence, I guess, that was brought up earlier from, I believe, Drew's question, where, you know, okay, like the relationship, I guess, between the multi-twist and a curve defined over suitable parentheses T. And so, yeah, if you're given any multi-twists, right, you can cook up some curve defined over suitable parentheses T that, right, that has stable degeneration. And, right, the tropical curve that you get from that carries the same data as this monodromy operator. Right, and so this result really largely relies on this étale Harris-Pultz theorem of Hein and Matsumoto, where they basically say that this Ceresa class, this L-adic Ceresa class, agrees with this like L-adic analog of the Johnson homomorphism. Okay. And then in the tropical setting, at least with integer edge lengths, it's a little bit more straightforward. So the relationship between a multi-twist and tropical curve with integer edge lengths, right? So this is similar to the picture I drew earlier, right? You have your, if you have a surface over here with your commuting Dehn twists, right? So this is T gamma is product over these T Li's to the power Ci's. Well, this corresponds exactly to a tropical curve, right? So the underlying graph is just going to be, right, the dual graph to the stable fiber. And so maybe if you want to not pass through algebraic geometry and just look at the you know, the topological setting, you know, if you want to go in this direction, you would just cut along each of these curves, right? And then the connected components will be your vertices, and then the loops will correspond to your edges. Right, so here the powers Ci's that appear here will be the lengths that appear here. So it's like, you know, C1, C2, C3, C4, C5, C6, right? And these, right, the course, you just map over the corresponding powers to the Dehn twists. So like, yeah, this is like L3, I guess, L2, L1, L6, L4, and L5. Right, so now the the Ceresa class of this tropical curve, say, let's call it gamma, right? This is just, right, the Ceresa class of the corresponding multi-twist. Okay. So, right, so our main theorem was that the Ceresa class was torsion for any positive multi-twist, right? So in particular, this means that the L-adic, from this correspondence here, this means that this L-adic Ceresa class is always torsion. And then also this tropical Ceresa class is always torsion. And right, so I guess this could seem perhaps a little bit disappointing because the original like Ceresa cycle itself, I believe, is known to be non-torsion as a cycle. So for very general curve. However, the sort of benefit for our class is that even though it's torsion, it turns out to be very computable, right? Like if someone hands you, for like low genus, say, a multi-twist on a low genus surface, you could actually compute by hand what the Ceresa class is, and also compute by hand, whether or not it's trivial. And so knowing that if you know that this class is trivial, or non-trivial, you know that your original Ceresa cycle is not rationally equivalent to 0. But then you could ask, okay, maybe there's a problem that maybe you killed so much information that this cycle would always be 0. And this, at least from the examples we've computed, this turns out to not be the case. So let me make this as a note. While nu of T lambda is torsion, it's readily computable. Frequently non-trivial. Right, and its non-triviality will imply non-triviality of the Ceresa cycle. Right, so perhaps I'll end this talk with an example that we did. Right, so what we were able to show was that the Ceresa cycle of a tropical curve with integer edge lengths is non-trivial whenever the underlying graph is K4. Right, and we actually also handled another case. We did a genus, an interesting genus 4 case, where you have this loop of 3 loops. Right, and we suspect it to be non-trivial in more than just these examples, but these are the ones that we actually computed. And so so whenever your underlying graph is, for example, one of these 2, right, regardless of what the edge lengths are, the Ceresa class is going to be trivial. Maybe let me try to sketch the computation. Right, so the idea is, let's draw our multi-twist in a way that makes it look a little better for the hyperelliptic involution. Right, so this is for K4, right? Any arrangement of multi-twists whose dual graph is a K4 will look something like this. And we're going to let tau be the involution given by a 180-degree rotation. Right, so tau just takes the surface and you just rotate it in R3 180 degrees. Okay. And so when you do that, right, at least for these 4 curves, right, you get back the same curve, but then this curve here will map up to this curve, and then this curve here will map down to a curve over here. Okay, so you can compute that, right, the Johnson homomorphism of TLI or TL, I should say 2. Let's call this curve 2 with tau, right, equals A1 wedge B1 wedge B2, where I guess I should define this basis. Right, the basis is the sort of normal basis that you draw. Right, so this is A1, A2, A3, B3, B2, B1. Right, so if you use the formula for the Johnson homomorphism, right, it's probably, you wouldn't be doing this, you know, right, like during a talk, but hopefully it's at least convincing that, right, if you just take this curve here and map it down here, and then use the this formula for the Johnson homomorphism, right, and then this simplifies greatly. And then finally, you could do Johnson homomorphism of TL5, or say this is 5. With tau, right, this is going to be something like minus A2 wedge B1 wedge B2 minus A2 wedge B2 wedge B3 plus A2 wedge B1 wedge B3. Right, and again, this is just you applying the very concrete formula for the Johnson homomorphism. Right, and then for everything else, right, you get that that bit is trivial. And so, okay, so if we isolate a certain subquotient of the area where the Ceresa class lives in, then where is it? Yeah, this expression here, you know, is the Johnson homomorphism of this product of Dehn twists actually splits up, like it acts as a homomorphism. So you just have to know how to compute. You just have to know what these two computations are, and then you add them up, and that's how you get your Ceresa class. And then to show it's non-trivial, it amounts to a linear algebra problem. It amounts to, you know, you have this action of t-1 on the space L mod H, right? The space L mod H is some vector space. And right, you can, like I did this in like a Macaulay tube, and you can show that it's non-trivial for maybe a particular choice of integral edge lengths. Showing it's true more generally requires a little bit more theory. But anyway, this is perhaps a good place for me to stop. So thank you for your attention.